Hi, I'm Antonio Sala, and in this video we are continuing our problem statement and motivation on the problem and the task of model fitting for classification. In here, we'll just discuss the role of least squares in all this, and the conclusion will be that such least squares is not as relevant as it is in ordinary regression function fitting with continuous output values. Let's see why. First, we'll recap previous discussions. When we have a classification problem, we have, let's say, a two-label set of data we want to learn. Hopefully, we wish to learn a perfect classification, just as this cyan curve, separating red from blue by, let's say, fitting a function so that we classify red when it is below a given threshold, and we classify blue when it is above the threshold. So we need to determine these parameters which influence the shape of the boundary. However, if perfect classification is not possible, then we may, in a deterministic interpretation, think on a loss function, for instance, saying that if I say red when it is blue, I will incur a cost of 7 units, but if I say blue when it is red, I will incur a cost of 2 units, and then my parameters must minimize that cost, for instance. We also had probabilistic interpretations in the sense that, okay, maybe what we wish to learn are the parameters so that in this block curve, for instance, we try to approximate the probability of passing a given exam as a function of the hours of home study that somebody enrolled in the course devotes to it. So the thing is that, okay, but in regression, we usually start with least squares. So this is the question. Why not sticking to just least squares? I mean, if I have some data, even if they are 0, 1, well, if they are 0, 0.5, 1, 1.5, or -4, I can fit least squares model by minimizing this loss function. But, okay, 0 and 1, once I assign numeric labels, then why not using just least squares? Because, well, the fact is that if my least squares model is linear in the parameters, as xi are known training points, then I can compute these regressors and then obtain these parameters theta, so it will be very computationally efficient, just a pseudo-inverse. Maybe it will not be so efficient for a more complicated parameterization of f, but okay, so why don't we use this to fit our numerically labeled theta? And the issue is that, okay, I mean, it may work, as it is a one-liner in MATLAB or in many statistical optimization software, then okay, we may try that as a first option. But in fact, even if it is easy, it is not the really sensible option in many situations. Why? Well, let's start with the MATLAB example that will help us initiate a discussion on the validity of this. I will have this xy data. Well, I labeled 1 and -1 so that, let's say, I will fit a model in this form. So my regressors will be x1 because they will be multiplied by theta 1, theta 2. So each regressor for each data sample will be a row, and putting all of them together, I will have a regressor matrix, and standard least squares fit is just multiplying the data by the pseudo-inverse of the regressor matrix, and then I get this theta. And as my data are labeled 1 and -1, my decision rule will be just the middle of them, 0, this thing. So when this least squares estimate is above 0, I will say that they are the positive samples, those with 1. And when it is below 0, I will assume that I have negative samples. Well, This seems simple, but let us see the results. The red circles are the training samples, and the line that I fitted with least squares is in blue. And well, in here we have the classification boundary, and then we see that these two training samples are not correctly classified. But okay, we see that if I had this function, then classification would be perfect. Or maybe I can move up a little bit my regression boundary, but okay, then just what we see is that, okay, naive application of least squares is not the best way to address the problem, maybe. So our conclusion is that, in principle, least squares in a deterministic setting for perfect classification may be a valid option, but F must be maybe more complicated, including sign or whatever stuff. So it will not be that easy to fit, because, adding sign stuff loses gradient information, because, the sign of F has zero gradient here, and it's non-differentiable in the jump. So gradient-based methods can be confused when trying to optimize this kind of indices. So in principle, if I have a flexible enough function, I may try least squares. If my function is very simple, such as a line, then it will be difficult to achieve perfect classification. But however, maybe a simple function with a different cost index can do, in the sense that this line, its sign, actually separates my training points with perfect accuracy. So somehow naive least squares should be modified to either cost index modifications, so that the optimal thing is the new line instead of the old one, or with more complex shapes of F that can fit ones and zeros and steps and whatever. So this is the discussion on perfect classification. It may work, but there is ample room for improvements. And then when we deal with imperfect classification, such as in here, well, the thing is that, okay, least squares is a somehow symmetric cost index. 1 minus 0 squared is the same as 0 minus 1 squared. So we cannot implement this kind of asymmetric loss function. So we would require modifying our loss function to be able to assign a different penalty to false positives or false negatives. And also, in probabilistic settings, when we fit least squares, we usually think on a statistic model in which the regressors are corrupted by normally distributed measurement noise, let's say. This will be normal 0 with some standard deviation squared as a variance. And then if we assume this, then the fit error, this stuff, well, it has a normal distribution, so its probability density function will be something times the exponential of minus r squared divided by blah blah blah, standard deviation, etc. So the log likelihood of this thing will be r squared. So the statistical interpretation of ordinary least squares is assuming that my true model has the parameterization I wish, but samples are corrupted by normally distributed white noise. No correlation between the noise in different samples. So under that setting, least squares fit is the optimal estimator from a statistical point of view. But, if we have a red-blue thing, heads, tails, and a coin, then okay, the kind of distributions governing that random phenomena are not normally distributed. The probability of passing an exam and my observation pass-fail is not something with a normally distributed random noise. Maybe the actual mark if the student passes with 8 out of 10 or 8.2 out of 10, then if I were fitting the actual numerical result from 0 to 10, let's say, of my student, then least squares may be an option with this statistical interpretation of some variability. But if I am just fitting pass, fail, then the Bernouilly distribution, the coin toss, is something closer to the actual mechanism that generates my data. So then, Bernouilly binomial formulas have not this likelihood. So in principle, the correct statistical interpretation, the maximum likelihood estimation of all this stuff, will not be associated to minimizing a quadratic loss function. In fact, given that minimizing quadratic loss functions may be efficient in some cases, linearly parameterized, under constraints, maybe I have quadratic programming setups, but there is some kind of intermediate, truncated quadratic cost function that can be thought of when discussing these things, in the sense that, okay, imagine that I have a training sample that is +1. Then, if my f were 1000, I would say that, okay, it's, very positive. This should add no penalty to my fitting. Or if my training sample were -1 and my function were -234, then maybe this should not add penalty to my fitting. But on the other hand, if my training sample were +1, but this f for my given parameters were -6, then maybe I wish to add penalty because this is a wrong fit, and the difference will be 7 squared, for instance. Or if I had -1 as my training sample output, and with the current values of my parameters, I had +0.5, then I would like to add 1.5 squared penalty. Then this kind of loss function is this one, and a cousin of this is used in the so-called support vector machines, and this is, the closer loss function I may get to the true least squares, that helps me adding additional flexibility to my function f, because the shape of f can be very simple and going up and down with no penalty, instead of just needing to fit exactly 0 and 1. I mean, this figure was obtained with some f that, for this point, for instance, can take a value of 200, and at this point can take a value of -2000. And then with this truncated quadratic stuff, we are not forced to move down this fitting point so that it fits to +1 target, or move up this one so that it fits the -1 target, while still keeping correct classification, in the sense that ordinary least squares will make a large penalty on this point. It's 199 penalty error. So in order to push down the fit to the least squares loss function here, it may spoil accuracy in here. So using truncated least squares that in some cases can be solved via quadratic programming can be a way to allow a better classification accuracy with simple model functions f. So let us conclude. In this video, we discussed the role of least squares in classification problems. If I have some regression vector times parameters in a linear expression, then it will be very computationally efficient. So, as it is one line in MATLAB, why not trying it? But the results can be disappointing, at least if naively applied, in the sense that, okay, my least squares fit may need some tweaking, or in here, I may have this least square fit, but in order to adjust given asymmetric loss function, maybe I feel like moving up and down this stuff. So naive applications of least squares is not good enough unless I have a very complicated function that can indeed fit 1 to these blue samples and -1 to these red ones and have this sharp decision boundary, but functions with sharp edges are not so easy to optimize. So these are the conclusions regarding perfect classification, or the imperfect classification regarding the inability to put asymmetric cost indexes if I am using formulas related to this, and the fact that least squares is the optimal estimator in a statistical sense if I have training samples generated with my model plus normally distributed random noise, but when I have 0, 1, heads, tails, then the statistical interpretation breaks. And as a last observation, we said that some developments discuss sort of truncated least squares solution via quadratic programming that can allow extra flexibility in my design. But at the end, the conclusion is that naive application of least squares to classification problems can be tried, but in most non-trivial cases, there will be better options. So those options will be discussed in forthcoming videos. For the moment being, we end here. Thanks for watching.